Pleasure to be here and give a talk myself this afternoon. I want to report on some work that I did with Leslie Reed, my co-author, retired research geologist with the U.S. Forest Service PSW, that did a lot of work on this paper. So basically, I would call this an applied hydrology talk. We're using Caspar Creek flow records to test peak flow prediction methods applicable to watercourse crossing design. Just a quick outline for what I'm going to talk about. Introduction, a little background information. The Caspar Creek site, Liz has already discussed that, so I don't have to spend a lot of time on that. The methods that we used, including the methods to predict peak flows, our results comparing the methods and the sub-watersheds in Caspar Creek, implications for crossing design, and some summary points. So first, I just want to say with the California Forest Practice Rules, that since July of 2000, foresters have to design permanent crossings on non-federal timberlands for the 100-year flood flow, as well as passage of sediment and debris. When I started in 1981, it was a 25-year event, and then in 83 it was a 50-year event, and in 2000 a 100-year event. So a 100-year event is quite a strict standard. If it's a Class 1 fish-bearing stream, obviously they have to be designed for fish passage. And when registered professional foresters estimate 100-year flood flows, they have to use the flood flow measurements, records that might be available, and empirical relationships using watershed data, and then modify that with direct channel cross-sectional measurements. The 100, just so we're on the same page, for a 100-year flood flow, it's a flood flow that has a 1% annual chance of occurrence in any given year. And we've heard today about some flows in the North Coast, Redwood region over the last several years. We really haven't had a 100-year flood flow for a very long time. We did have one in the Central Sierra in January 97, the New Year's Day storm. But we haven't had an 80 to 100-year event in North Coast for most of the region since December 64, the legendary 64 photo, and here we show the Eel River. We do, unfortunately, have a lot of examples of failed watercourse crossings from lesser storms. 3 of these are from the coast region, the Redwood region. Also included on the top right, a photo that Mike Furness and Sam Flanagan have shown a lot that I always liked. It's from Gifford-Pinchot National Forest in Washington. So for the reasons for this study, we think that more information is needed on the accuracy of commonly used methods that foresters use for designing watercourse crossings. The best way to test the validity of these approaches is to compare them to measured stream flow data. Most forest crossings, and we've been monitoring forest crossings for more than 20 years, a heck of a lot of them are in small headwater streams. Many of them in Class 2, Class 3 streams that are intermittent or ephemeral and often have drainage areas less than 200 acres. So the problem is we don't have that many long-term gauging station records to test these methods. We don't have a lot of gauging station data in these very small watersheds, but luckily we do have a long-term data set from Caspar Creek. Liz has told you about Caspar Creek, and I know a lot of you know a lot about it already. It is the site of a long-term watershed study between CAL FIRE and the PSW since 1961. The experimental watersheds are located on Jackson Demonstration State Forest, site of 2 experiments, the South Fork in the 70s and the North Fork late 80s, early 90s, and a 3rd experiment currently planned. Is second growth and third growth coast redwood and Douglas fir forest, as we talked about, 46 inches of annual precip, steep erodible terrain subject to landslides, as Liz told you about a few minutes ago. Well-drained loam soils, mostly in soil hydrologic groups B and C, and anadromous fish streams. The weirs at the North and South Forks were built in '62, so we have a long 53-year record of flows, peak flows in both the North Fork and the South Fork, and we expect to continue to monitor with a long-term agreement with the PSW through at least 2099. Just a couple photos here illustrating differing winter flow conditions at the North Fork. large peak flow in the rectangular part of the weir on the left. The 53-year record for the North Fork, you can see we had 40-year events in 1966 and 1974, but nothing of that magnitude since those years. So we're still waiting for a very large flood. For our study, we focused on the North Fork, where we installed headwater monitoring stations in the summer of 1984. I enjoyed helping build those stations that summer, and we put headwater stations in 8 tributaries, and 5 of those have continued to be monitored for the 31-year record. And the control watersheds shown here in red are Ive and Hen. The clear-cut subbasins are Eag and Carr, shown in brown, and our partially clear-cut watershed is Dahl. These are all less than 200 acres in size. 4 of the 5 are less than 100 acres in size. The clear-cut basins, Carr and Eag, almost 100% clear-cut, just a very minor amount that was left for buffer strips, wilpizes. And this is what it looked like in 1991. You can see the control Sub-Watershed HEN, 96 acres with the bottom arrow there, and the clear-cut Sub-Watershed Eag on the right. Just a little better view of Eagle or Eag in 1991. It was not a fuzzy clear-cut, one with nature nooks or anything like that. This was a knockdown, real clear-cut like we did in the old days. We measured stream flow, and I think Liz already covered this with wooden partial flumes in the early years that we built in 1984. These are the wooden partial flumes at Carr on the right and Eag on the left. And then 2004, replaced those with fiberglass Montana flumes. The December 2005 storm that was talked about, Sub-Watershed HEN, one of the controls shown on the right panel there. Sub-Watershed Ive, the other control, smaller watershed with the fiberglass Montana flumes. And lastly, our partially clear-cut Sub-Watershed Dahl with the wooden partial flume on the left and the fiberglass Montana flume in the December 2005 flood event. Bob Zemer looked at changes in peak flows for these clear-cut watersheds, headwater tributary watersheds, Carr and Eag. He had almost a 30% increase in peak flows for the 2-year recurrence interval flood event, then some nice recovery over time, recovering in about 10 years, or would have recovered in about 10 or 11 years, but we did some pre-commercial thinning, reducing the canopy, and then elevating peak flows again at that point. The 4 methods that we tested for predicting peak flows were the rational method, the USGS magnitude and frequency method, flow transference methods, and the NRCS TR55 program. The rational method has been around for more than 150 years, used a lot still in urban settings, and foresters are still using it a fair amount as well. It is limited to small watersheds, less than 200 acres, and performs best less than 100 acres. But it is Q equals CIA, C is the runoff coefficient. Typically, we suggest something like 0.3 for forested watersheds. It can be as low as 0.2 for a 10-year event, and the literature even suggests as low as 0.1. I is the rainfall intensity in inches per hour for a storm of a given return interval, and A is the drainage basin area. You do need to obtain the time of concentration to get at the rainfall intensity, and the time of concentration is simply how long it takes water to go from the top of the ridge down to the crossing site. There are more than 30 equations in the literature to predict time of concentration. We tried the age-old Kerpek method that's been around since 1940, the airport drainage method that was FAA in 1970, and a British Columbia Ministry of the Environment nomograph that was developed in 1991. These yield widely varying time of concentrations. The Kerpek method is basically for overland flow, so it comes up with a really short time of concentration for Sub-Watershed HEN at 6 minutes. We think a more realistic estimate is the British Columbia Ministry of the Environment nomograph coming in at about 45 minutes based on estimated movement of water on these hill slopes and stream channels. Once you have the time of concentration, then you can get the 100-year precipitation for that time of concentration. We suggest using the NOAA 14-point atlas for rainfall depth duration, frequency duration data, and that is available online and very easy to use. The second method that we tested is the USGS magnitude and frequency method. Godwald et al. Updated these in 2012, replacing the old Wanahan Crippen equations that were around since '77, so they do have updated data, include some more recent flood events. There are equations for varying recurrence intervals and equations for 6 regions of the state, and they're very easy to use. All you need for the North Coast equation is the basin area and the average annual precipitation. Easy to use, broad brush, because the areas in the state are large. For Caspar Creek, we use the North Coast region. You can see it's quite large there in blue. It is the method that's used for the USGS Stream Stats program that's quite widely used throughout the United States. The third method is the flow transference methods, basically adjustment of drainage area method. It's used where we have a crossing site, and then downstream from that crossing site we have a lengthy gauging station record, or perhaps nearby in a hydrologically similar basin, a fairly lengthy gauging station record. And you adjust the 100-year discharge for the gauge station for the difference in drainage area between the ungauged and the gauged using a simple equation. And this does generate the highest confidence in the results because it's using local data. So here's the equation. It's fairly easy to use. The area ungauged divided by the area gauged, just prorating that, and then raising it to an exponent for drainage area. And that is because small watersheds are more flashy than large watersheds. If you do have a really small watershed, say less than 2,500 acres or 1,000 hectares, you can drop the exponent for drainage area and just go direct with the ratio of area ungauged to area gauged. And we did these, just an example here of watershed hen, dividing the area of hen 96 acres by the area for the North Fork Weir 1169, and then multiplying the 100-year flood flow. The last method we tried was the NRCS TR55 program. This is based on SCS curve number methodology that's been around since the 1960s, maybe the 1950s. Curve numbers range from 0 to 100, and the value depends on the land use and the soil hydrologic group that is in the sub-watershed. It's used commonly in the coast region for vineyard conversion projects, so if you have detention ponds or small reservoirs, it's a good method to use for that. And it does do a pretty good job of getting a relative change in peak flows. So if you want to know what soil hydrologic group you're looking at, you can go to the NRCS Web Soil Survey online, look at the soil series, and make an estimate of the percent each subbasin has for each soil hydrologic group, and I did that for the 5 sub-watersheds. So for results, and we did this test for the 4 methods for 10-year flows and also for 100-year flows. We tended to put more reliance on the 10-year flow estimates because we haven't had any very large events in the Caspar Creek sub-watersheds. But the results are shown on the bottom here for the 10-year flows. Fairly small numbers, 16 CFS for Sub-Watershed HEN, and the 95% confidence limits below that. We use the USGS peak frequency program to do the flood frequency analysis for the 5 watersheds, sub-watersheds. This is the 31-year record for Sub-Watershed HEN. You can see that the flood record was the December 2005 flood event, coming in at about a 20-year event in this watershed. We ran flood frequency curves using USGS peak frequency for all 5 watersheds. You can see only minor variation around the best fit model using a log Pearson type 3 distribution, and really quite a good fit for the data for these 5 watersheds. If you look at the comparison of 10-year estimated flows from the methods I talked about compared to the flood frequency analysis estimate of 16 CFS, the commonly used methods by the foresters come in a bit higher, some of them quite a bit higher. The direct flow transference did the best at 19 CFS, and the rational with the BC, British Columbia nomograph, and the rational with the airport drainage did reasonably well. We have in the paper these plots of 10-year values for peak flows and 100-year values for peak flows for each of the 5 watersheds for each of the methods. And you can see that the poorest ones were the NRCS TR55 and the rational, the Kerpek method. The best, again, were direct flow transference and standard flow transference. If you look at the percent over prediction for 10-year flows, average for the 5 gauging stations, it was 380% over prediction for the Kerpek with the rational method, only a 17% over prediction for direct flow transference. The others that did reasonably well were standard flow transference and rational with the BC nomograph and the rational with the airport drainage. In 1995, Carl Yee, who was then a professor at Humboldt State, did recommend using the airport drainage method for time of concentration. So that has been recommended for a while. If you plot, and we did plot the 10-year and the 100-year estimates for flows for the 5 gauging stations, the results are quite similar for the 100-year flows as would be expected for the 10-year flows. Nothing significantly different there. Same general patterns. When we looked at the prediction for the 5 sub-watersheds, we were curious if anything would shake out there, and 4 and 5 had similar over predictions for all the methods, but watershed I, the control watershed, was quite a bit higher and had the poorest predictions of any of the 5 sub-watersheds. We think that that's probably due to larger contributions from groundwater or subsurface matrix flows, possibly due to old landslide deposits in Ive. Study was inconclusive whether the changes associated with the clear cutting in Carr and Eeg were large enough to affect crossing design. We didn't feel like we had enough data to actually make a strong statement on that. Here are the 5 sub-watersheds with the percent over prediction for the 10-year flow by method. The implications for crossing design, each method has different data requirements. Obviously, some are going to work better than others depending on what data you have. You may not have a downstream gauging station or a gauging station nearby, may not be able to use the flow transference methods. We suggest using several methods, if at all possible, and evaluating those for uncertainty, model uncertainty. And the office results always have to be field checked and make channel cross-sectional measurements. In the coast region, you can try the 3 times bankful stage method, and it should give you a reasonable determination if your office method is actually accurate. And you also have to design for wood and sediment passage. Sam Flanagan works for BLM out of Arcata. Collected this data in 2004 for storms that were less than 12-year recurrence interval. 57 failed crossings, almost 80% failed due to woody debris or wood and sediment. So hydraulic exceedance alone rarely causes crossings to fail in the Coast Redwood region. You need to design for water, wood, and sediment. Greg Bundros, retired from Redwood National and State Parks, had this photo in the Redwood Creek Basin illustrating this concept of wood blocking entrance. Mike Furness and others a few years ago illustrated ways to reduce the risk of crossing failure, having the headwater depth pipe diameter ratio less than 1, having the pipe roughly the same width as the active channel, having the pipe as the same gradient as the stream channels, we don't get bed load dropping out at the inlet, and having the pipe appropriately aligned. In the last 15 years in the Coast Redwood region, we've moved away from culverts to some degree, still probably putting in 70% culverts, but we have a lot more bridges, open bottom arches, and rock armored crossings. And these are much more forgiving for passing wood and sediment, better for fish passage, for bridges and open bottom arches, and they are not as sensitive to errors in predicting 100-year flood flows. These concepts are covered well in PWA's revised Handbook of Forest and Ranch Roads. We are covering them in our revised document we put out in 2004. We have a new version that we're going to release by the end of this year. We're designing 100-year flood flows for wood and sediment, and it will cover bridges and rock armored crossings. Don Lindsay has written those chapters from CDS. So just in summary, we tested 4 estimation methods at Caspar Creek. They produced widely varying results for peak flows. Rational method can work well with the appropriate time of concentration and runoff factors. Flow transference methods provide the most accurate methods. USGS equations produce better estimates than the TR55 program. We suggest using multiple methods if possible. Do need to check the results against channel cross-sectional measurements, and we do need to design for wood and sediment passage as well as fish. And a lot of people helped over the years on this guidance document and the one we're working on in this paper, and I want to acknowledge all of those folks. Thank you.